All right, we're on, and what I'd like to do is address a question that Kif sent me, and let's see, I will switch to a window that I started earlier. Come on. All right, so this is the exit program, and if you try to modify this program and use return, it doesn't behave very well. And the question is why? I assume, are you seeing this thing yet?
I am seeing it.
All right, so let's see what happens when you run the program. Set a breakpoint, tell it to build a program. Now we're on that line. And we really don't have to do any more than look at things at this point. Suppose that you try to return from this. Where is it going to return to? You see the register window?
Mm-hmm.
Yeah.
All right.
Yes, the
so
bottom.
It has some stuff for a stack, right? RSP. If we look in the data window, I think I can drag it into view. It has the stack, at least some of it displayed. And what are the parameters to main? Does anybody want to make a guess?
You can define your argc and your argv, I guess, if you wanted.
Exactly. And I ran this program without adding any additional things, so argc is a 1. Here it is on the stack. argv is this pointer, which is certainly going to be some form of name of the program. All right? So on the stack, we've got these things. If we had made a function call to enter start, then the return address would be the top thing on the stack. So if we try to return from this thing, we'd be returning to an address of 1. Does that make sense? So if you try to do the return instruction with a stack like this, then you're returning to an address that's 1, which is going to be an illegal address. And the answer is that this program, oh, did I have a, oh, that's cool. I hadn't paid attention. I may have to use this feature. I was thinking I might have put some of these dock windows where they could be, or all of the dock windows where I could move them to the bottom of the screen or something. Yeah, that might be useful. All right. So had it made a call to the function, the return address would have been put on the stack. But this function start is a little unusual. It has 2 parameters, which are argc and argv, but they're not done like normal C parameters for C functions or C++ functions. Because normally they'd be placed in a couple of registers. Instead, they're using the more or less historical pattern, which is to put the parameters on the stack, and returning doesn't make much sense. Is that logical? So you learn one little fact. Can't return from start. So where do you return to when you return from main?
When you return from main, you exit the program and you go back to the shell,
Well,
right?
Not exactly. There's still a little bit more to derive from this. You don't really exit the program when you execute that RET statement that's in main. You return to perhaps underscore start or maybe some other function that was called by start. So start is the actual first piece of code that's executed when Linux runs a program, or underscore start. And it's not a normal function, right? And it has no way of returning. If it did return, it would be needing to execute a return that returned from user mode to kernel mode. I don't know if the CPU supports doing that or not. It possibly could, but that's not the way it's organized with Linux, right? So to do anything from that function, you need to do a system call to get something done, and to end the execution of the program, the exit system call, or possibly something that fails, where to just give an error message and die. All right, we have other questions? No. All right, open a file in this tab.
Dr. Ray, just to clarify, I think that question came from KG, not from myself.
Oh, I forgot. Sorry, you're right. You must know that you didn't do it.
I was trying to figure it out for a little while.
Sorry. My memory is moderately good, but I can't remember all things. I can remember a small subset. All right, so here's an add program. Doesn't have much in it. Ooh, there's a lot of junk in here. It's bigger than I thought. That's too big. Let's try a different one. I want to get something simpler. Discard that. How about add one.asm? That's a little more like it. Now we can see some code, and we can understand this one fairly easily, so it'll be fine for our purposes. All right, so when we do execution, this is an instruction that moves an address into a register, and as I discussed in a previous tutorial, this won't assemble on OS X because the address of A under OS X is too big. So if we execute that instruction, the address of A is hexadecimal 602088, and in OS X that would be something like maybe 1 and then an 8 hexadecimal digit kind of number, some number that's bigger than, 8. 8 times 4 is 32. So something that's bigger than a 32-bit integer can hold. And the field in the instructions for this move would be a 32-bit field. So it works with Linux, but doesn't really work reliably if you're going to go between computers. So you should use load effective address if you want the address of A. If you want the value of A, you can move with bracket A. So now we've got A is hexadecimal AF, and a right click on that, we can change that format to decimal. And then we have a an add instruction. And since we've got an expression of some sort in brackets, is going to go to memory at the address specified and get the value from there. And since we've given it RAX, it's going to get a 64-bit integer from B. And if we execute that, now we get 4272, which I assume, it has to be right. All right, so that's most of what you can do with add. You can add register to register. Can we add to a number in memory? Let's give it a go. How about add to B, RAX? I think I'll comment out the line there. That makes more sense. And let's see what we've got in data. We'll define B in a moment. So now we got the program running, and I'll double click on B and then right click, if I can do it, yes, define variable, and it's a long and I will define it to be printed with decimal and OK. All right, B is now 4097. Let's see if we can get away with adding to it. We've moved the 175 into RAX, and we've inverted this. Hey, now we put it into memory, 4272. That's pretty convenient. So what else can we learn about the add instruction? The flags register. PF is what, parity flag?
Page file?
ZF and IF. I accidentally clicked one too many times. It has done XOR, RAX, RAX, which put a 0 in RAX, and ZF, or the 0 flag, is now set. So a 1 in the 0 flag means the number was 0. Let's run it again. I don't think the move changes the flags. Still got 0 flag set. Now when we do an add, it should change it. So now we have the, what is AF? My memory's weak. The IF is interrupt enable flag. AF, I'm going to cheat.
Looks like, oh, hold on, I just set it up. Adjust flag?
Adjust flag. Oh, okay. I don't want to know much about that. I think you must be right. The instruction set has capabilities which are useful for implementing binary coded decimal arithmetic, and I think the adjust flag would have some utility in that. I don't really want to think about it. There's way too much to know to try to know all of that junk if you're not going to be using it.
Yeah, it looks like it's related to an arithmetic carry.
Yeah, so it's like if you did some arithmetic with a binary coded decimal nibble, and then you got the adjust flag set, then you would add 1 to the position that is higher, I guess, or something like that. I don't know how to do it exactly, but I could look it up if I really had to. All right, so we've seen then that 0 flag is not set. What about negative numbers? Well, let's change this to A is a negative. Oops, that's not a negative. Negative 175. Run it again. Oh, that's not going to set it with that. Let's make everything negatives. Start it over. Now when we move the value into RAX, it hasn't set any flags from that instruction. And when we do the add, oh wow, look at all the flags. We have the carry flag, the parity flag, the adjust flag, the sign flag, and the interrupt flag. And the one that matters for our purposes is the sign flag. The sign flag says the sign bit on the result is a 1, which means that it's a negative number, right? And if we go back to the data, we should see negative 4272. So we've learned what you can do with an add. What about subtract? The picture is much the same. Let's see. What are we going to get when we do this subtraction? Is it going to be 4097 minus 175 or 175 minus 4097? And the answer is yes. It's going to be one of those two, isn't it? So what number is a positive result? If it were to do 4097, we'd get a positive number if it was the first thing minus the second thing. But the answer is, where is the value? Oh, it's in B, 3922. I thought that was the other way around. Thought it was going to be the second item minus the first item, but it's B minus RAX apparently, right? Don't want to argue with reality. We run it again, I think we get the same thing. So we have B is 4097, and if we keep executing, we do the sub command, now it's 3922. It plainly subtracted in the pattern that I had not expected. That's weird.
Surprised me too, I guess, the other way.
Yeah, I thought it was the other way because it generally seems backwards to me. I would prefer it be in the other order, and there is another order available. It's AT&T syntax, or I think it's, I don't know which one's which. One of them's Intel, one's AT&T.
Could you specify a third operator? So I know in ARM syntax you can tell it which ones to subtract, and then a third one to
Get the result? No.
get the result in.
I'm pretty sure that sub always has two parameters. It doesn't have a 3-operand sub, though it does have, with the AVX instructions, they added the ability to use 3-operand syntax. So if you're doing a floating point subtraction, you could tell it with, I think it's V sub SQ for sub single quad or something about like that, that it would be, you could put a third parameter in, so that actually the first one of the three would be the destination, and then there'd be a subtraction. If I were going to be doing subtractions, I would be checking it with EB fairly, close to the point when I did the instruction, because it doesn't make sense. The assembly language doesn't look like arithmetic, and we're used to thinking in terms of algebraic notation. There's no resemblance, so it doesn't feel natural. If you did a lot of it, maybe it'd feel more natural. All right. Add, subtract. Oh, there's a negate instruction. Let's try a negate. Oops, I tried. All right, so now we've got the negate instruction, NEG. So we need to look at the register, since I did negate with the register, and now it is negative 175. So that did its thing, and it should have set the sign flag because it made the number negative, right? It did that. And that's about all you can say about that. Carry flag, we're not going to have a lot of value in carries. Carries would basically mean you've had possibly an overflow. It depends on the circumstances. So you could test that for having an overflow of arithmetic. All right, so we've got a negate. Can we do negate with B? Oops, if I could type a bracket, maybe. So, oops, invalid size for operand 1. It's not happy with me. Let's bring that up. I don't know if you saw the error. I think I have to drag it on top of the window. Now you can see the error, right? Trying to get used to this stuff.
Yes. I can see the error.
All right.
Error box.
So I made a small boo-boo. I don't think that it allows you to use memory for a negate instruction. It was my guess that it probably works, but it apparently doesn't. Add, subtraction, I guess the next thing to try is multiplication. I believe there is a mul instruction, but I favored imul. I think mul is a multiply with ignoring signs, but it's been a while, so I don't remember precisely. So let's do RAX 10. And let's see. Stepping forward, we move the value of A into the register. We got 175, and we multiply. Come on, we multiply. Did anything else happen? I don't think so. All right, let's see. There is one form of the multiply which has, and I'm going to cheat and look at the book, Ben, so I sounded funny. There's a one operand multiply, I believe. Yeah. And about the only way a one operand multiply would work would be if you were to multiply and specify something to multiply something else. So let's run it with just a 10, see how this behaves. Invalid combination of opcode and operands. I will save time by just looking it up. Chapter 6. All right. One operand multiply says multiply RAX by data. Apparently that works. I thought you could multiply by just a constant. Says note that it requires the quad word attribute for the source for the single operand version, which uses memory. And apparently we can't use 10. So I'm going to try it first with just multiply this by B, and let's see what happens. I'm not putting the Q word in like I just read that I'm supposed to do. Invalid size. So there's some sort of default size, and it's apparently not correct. Q word, a quad word, or 64-bit integer from B, and now the computer's happy. All right. We're about ready to do the IMO. Observe the registers and tell me what all changes. Got it memorized? What changed?
RAX.
Anything else?
RIP, RIP.
Well, RIP modified. That's good, yeah. Let's try it again. There's one more that's changed. You see it?
I think it's
RDX.
RDX. That's correct. RDX contains the high order bits of the number. So let's change this so that instead of by doing 4097, let's multiply it by, oh, how about Is that 1 billion, or do I need some more digits? It looks like 1 billion to me. Let's try it and see what happens. Oh, I need a bigger number, don't I? Oh, it's a 64-bit integer. How big a number do I have to make it be to make it into the next number? Ah, finally I've got too big a number. Let's take a couple of digits off. Oh, there we go. We got a 9. Hexadecimal 9 is, see, 175 is, what is that? 120? I don't know. I'm trying to remember what the hexadecimal values are, and I don't remember very well. Run it again. Oh, well, the result is multiplying by a decimal number. Let's multiply it times a hexadecimal number. That way we'll preserve the bits of 175, just shift them left a whole bunch. All right, so AF is a 175. We multiply it times, that is a 1 with 8 zeros in hexadecimal, is that right? I think that's 8. Not enough. We got AF, but we need a little bit more. Let's see. Try it with that thing with a couple more zeros. These big numbers are strange. I'm not used to manipulating 64-bit integers in my head, so I don't have a good feel for just how big the number has to be to make it over into the next half of the product. A couple more zeros, and I'm going to get tired of this. All right, so we managed to multiply it enough that the A made it 64 bits to the, or made it over to the left. So it must have gone about 60 bits to the left. If we do one more zero on this number, we'll get the A and the F into the high order thing. Oh, it says that doesn't fit. Can't do it with that big a number. Let's try doing it with almost that big a number. How about F? That's still too big. All right. What do you know? The number has in the top half a bunch of F's. Right? Is this enough to be a negative number? Let's try doing this. Change it to decimal format. It is. It's a negative 11. So the number's negative, but look over here in the flags. We don't see the sign flag set. That's weird. I didn't know that it did that. One operand mul. I don't know that I even mentioned what flags got set. All right. There are a couple more flavors of imul, but this is a good one to think about because this one uses a 128-bit combined register, RDX, and they usually specify it as RDX colon RAX. So the product goes in there. If you want to do division, you put a 64-bit, what do you call it, the divisor, dividend, and quotient, right? So the dividend, I guess, is the other number. So you put a 128-bit number in RDX colon RAX, and then you do IDiv to divide. All right, we have questions about any of the arithmetic so far? All right, what about the this is a single word IMAL. When you do the other IMAL, how about we do RBX, not RF, RBX, that's not even close. And we multiply by 10. I think we can do that. All right, and it's not in RBX. What happened to me? Executed the IMAL instruction. Does anyone know why we didn't get the result in RBX?
What was RBX before? Like when the program started?
I was thinking of multiplying the 175, and I didn't put that into RBX, right? So let's move the number into RBX. Thank you. I was getting confused by some absolute silliness. If I could type, that'd be dangerous. All right, so now we've got a move that puts it into the right place, so it will behave like I think it should. All right, so now we've got two AF registers, and we get a 6D6. That doesn't look like 10 times AF, but it probably is fine. We could change this to a 0x10. That's an x0, 0x10. I don't really want to see that extra thing there. Now multiplying it by a hexadecimal 10 is the same as shifting it. Oh, let's see, run it. All right, so multiply it by a hexadecimal 10, we add a hexadecimal 0. All right, so that's the 2-operand IMAL, and there's a 3-operand IMAL. That one is rather goofy because it's not like Brandon had mentioned about 3-operand where you choose a destination. Though it's kind of like it. You choose a destination. Yeah, I guess it's maybe it is very much like it. So let's get rid of this move instruction. So now we've got 3 operands, and you have to wonder if it does this. Why did they do that? So this one is multiplying RAX times 10 and putting the result in RBX. So this is the famous 3-operand syntax, right? Where you have a separate destination register that's not part of the operands for the instruction, or not part of the operands for the mathematical operation. I don't know why they did it for IMAL and didn't bother with doing it for anything else. It's part of the absolute nonsense about the Intel instruction set. It evolved from a very simple instruction set that was specialized, and it has warts. This is, I guess, one of the warts. All right. For this one, pretty sure the destination has to be a register, but Um, let's try multiplying B, which is going to have a hexadecimal F, or 15 in it. So we get F0. So yes, now we got 15 times 16, which is 240, I guess. A cheap thrill. Can we multiply one memory address times another memory address? Syntax looks good. Computer says invalid combination of opcode and operands. I'm fairly sure that none of the instructions allow you to specify two memory addresses in the same instruction. How big a number can we use for the number that goes in the right side of this? Well, let's just accept the thing that's given there. Will it do that? No. It told us the truth. Value does not fit in signed 32-bit field. Oh, 32 bits would be about, well, that's probably okay. That looks like a, is that 8? That's one too many. Let's try multiplying it by that many. Doesn't look too reasonable as hexadecimal. I mean, as decimal. Change it to hexadecimal, still pretty ugly. What went wrong with this? Let's try and multiply it by a slightly smaller number. Oh, B was, multiply B, which is an F times that. That's pretty crazy. Our BX has an F0. Oh, is it not putting the product into RDX and RBX? The only one which does the combination register for 128-bit result is the one operand IMAL. The 3 operand and the 2 operand IMALs don't modify additional registers. So the product for this thing is placed in RBX, an F with 6 zeros, and it doesn't modify any of the others. There's no other register that pairs with RBX. The only pair that I'm aware of is RAX colon or RDX colon RAX. Those two are paired up for multiplication and division. All right, so if we're going to do a division, which I guess is next, we need to place, at least generally, I don't know what the heck we got to do. Oh, I got to tell it not to do the completion. I think you can tell it not to complete with an escape character. Let's see. Escape. Yeah. W, escape. All right. It's hard to remember these details. I do my editing normally in VI. So even though this editor is okay, it feels clumsy for me. So if we want to divide, we need to zero out, which I guess I need to do with XOR, RDX, the high order, and I'll use EDX. Oh, how much difference is it if we use XOR RDX, and XOR EDX, EDX. Both are possible. They will both do the same work. So let's stop right here for a moment, and I'm going to use the terminal window. This is add 1, I think. Yes. So I'll change to my terminal window. It's going to be a little ugly, but I think you'll be able to read it. Oh, I'm back alive. Now there's the one I want. All right. So now we can see the instructions for XOR RDX, RDX, and XOR EDX, EDX. The only difference between them is the XOR with RDX begins with a 4/8 hexadecimal prefix. The rest of the instructions is the same thing. This is part of the evolution of the instruction set. Seeing these binary or hexadecimal values is not that important, but you may as well remember that you can zero out a 64-bit register using its 32-bit portion, because you save 1 byte in the instruction space of your program. How much difference is it? Well, 1 byte. Does it matter very much? It's a slight drag on the program because it's using up 1 byte of the instruction space, which uses up 1 additional byte of the cache memory of the computer, right? And it may not be very clear to you, but the memory of the computer is a whole lot slower than the CPU. How fast can a number be moved from memory into a register? Anybody know how long the latency is for memory?
Isn't that related to the cache latency?
Well, just saying it has to come from memory. So how much is the memory latency? You can chase it down with Google.
Mm-hmm.
See if anybody can type faster than me.
Four nanoseconds.
How much?
I'm just guessing. I thought I had read somewhere 54 nanoseconds.
54 nanoseconds.
I was reading on context switching.
SDRAM latency. Let's see. Do they have some actual numbers?
It says in asynchronous DRAM, the interval is specified in nanoseconds, absolute time. In synchronous DRAM, the interval time is specified in clock cycles.
It's in clock cycles, okay. So let's see, SDRAM access timing. There's a row access, 3 clock cycles, a clock access. It looks like it's going to be like 12 cycles or something. So it says, for example, latency value is given as 2.5, 3, 3, and 8 would be, I guess you add all those up together, which is about 16 cycles. All right, so how much difference does that make? What can the computer do in 16 cycles?
Presumably 16 instructions.
Yes, it could do 16 instructions, but not if the computer has to spend 18 or so of those cycles fetching an instruction from memory, right? So in order to get one or more instructions per cycle, it has to be possible to beat that memory bottleneck, right? So if the memory bottleneck costs 18 cycles, then there really isn't any point in having a 4 gigahertz CPU. You can have a 500 megahertz CPU and do okay if you're stuck with that kind of memory access time for every instruction. But if you repeat instructions the second time around, your odds are pretty good that the instruction is going to be in cache and you'll suffer no real delay in using that, right? Even with cache, that's not as quick as the registers of the instruction set. Registers a little bit faster than cache, and if your instructions are in cache, your data's in register, you can do some pretty good results. I believe in my best result was using AVX instructions. I think I got 6 floating point results every cycle. I was not bringing the data from memory during doing 6 of them in a cycle. It operated on 4 of them at a time, but got 6 in a cycle, so it must have been using pipelining with the AVX or something. I'm not exactly sure what, but it was pretty good. All right. Do you have any other questions? See, back to the program. Hey. I'm not real used to this trackpad on my keyboard. I can double click sometimes on the pad and it works, sometimes I don't. Sometimes I click, I get the equivalent of a 2-finger choice, which is a right click. That's annoying. All right, so let's see, we moved a 0 into RDX, and our purpose in doing that, one little purpose was to show that you can save 1 byte by using EDX, and the other purpose was to get ready for division. So let's move a number. Let's try B. Excuse me, move into, let's see, RAX. And let's do IDIV. Does it have one operand for IDIV? Let's see how it likes me with this. I didn't remember. Invalid combination, line 12. Yeah, it doesn't like that. IDIV. Apparently you got to supply at least 2 operands. Let's see if that's correct. No. Let's see. B, that number is not too good. RBX, RAX, B. So I had a 175 in B, and IDIV RBX. Got nothing in RBX. How about EBX? Run it again. I don't think I got it rebuilt. All right, so we got a 0 in RDX. We've got a 175 in RAX. Excuse me, an F in RAX. We're about ready to do the division by 10. Son of a gun, it did do that. All right, so let's make it a little more entertaining. Getting a 1 for the result is not that exciting. So we moved B into RAX. How about if we That number would be nice. 1, 2, 3, 4, 5 hexadecimal. All right. All right, so we're going to divide that big number 1, 2, 3, 4, 5 hex by a 10, and we get 1D20 for the low order half of the result, and we get, is that the high order part of the result, or is it just a 5 that's been hanging around? Let's try changing this one to decimal format. 7456. We get a quotient and a remainder, right? Oh, that was a hexadecimal value. Let's run it again so we can see what the number was in decimal. Dividing by 10 is much happier in decimal. All right. Move 10 into RBX. So now REX has 74565. One more step, I'll be kind of tired of things. So you can see we divide it by 10, we get 7456. And when we did the division, we got the quotient in register REX and the remainder in register RDX, right? So if you do a division, you get both results. You don't normally use them both, but if you're in assembly language, you can use them both rather readily. Probably a C compiler would be intelligent enough to take advantage of the quotient and the remainder being both available. I would bet on it being better than me. That's been my experience in the past. I've written some code that I was really proud of because it was long enough to time and used nested loops, and I had everything in registers that I was using in there. I had a memory address in a register, and I had incrementing in registers. Everything was done with registers, and I wrote the same code in assembly, and in C, the compiler beat me by about 5%. And we looked at the code the compiler had generated. It used the stack to store some of the temporary results where I had stored them in registers. I figured registers would be better than the stack, but obviously the compiler writers know more about the instruction set than I do. All right, any questions about this arithmetic that we've got here? I think it's a good stopping point. Seeing the division and making sense of that's good enough for me. All right, appreciate the question, KG. I'm not sure if KG's here or not. Hey, we got Mike. All right, thank you, and I guess I'll see some of you again next Monday. Bye.
Yep.
Take it easy.
Thanks, Dr. Safer.
Take care.